Welcome to this presentation on an EFCM mobility prediction model for resource allocation in mobile cloud computing. This research was conducted by Praveena Akki et al. And published in 2021. Today, we'll explore the key findings and contributions of this important work. Let's begin by understanding the problem this research addresses. Good morning, everyone. Today, we delve into an efficient mobility prediction model for resource allocation in mobile cloud computing. The theoretical gap we address stems from the inherent challenges of user mobility in mobile cloud computing environments. While cloudlets offer a localized solution to high latency and low bandwidth issues associated with distant cloud servers, their effectiveness is severely hampered by dynamic user movement and fluctuating wireless signal strengths. Existing resource allocation methods often fail to adequately capture these complex user mobility patterns and, crucially, neglect critical radio propagation factors such as path loss and shadowing. They typically assume a stable connection within coverage, which is often not the case in practice. Our central hypothesis is that by integrating the user's historical access patterns with real-time radio propagation characteristics, we can proactively predict future access points, thereby ensuring continuous connectivity and optimizing resource allocation. Our baseline assumptions include that mobile devices are constantly in motion, leading to dynamic network topologies, and that while radio propagation factors are complex, they are location dependent and can be modeled to inform connectivity decisions. Our proposed methodology introduces a connectivity-based mobility prediction algorithm. The core mathematical framework begins with a system model where the next access point is predicted by considering the user's past accessing history and radio access connectivity. We assume a constant user velocity for this prediction. A critical component is the signal to noise ratio, or SNR, which is calculated using a formula that incorporates the standard deviation, the transmission power, the path loss factor, and the additive white Gaussian noise. A connection is only established if the obtained SNR value meets a predefined threshold, specifically 40 decibels in our model. Path loss, a significant radio fluctuation factor, is quantified by a formula involving the antenna far field reference distance, the total distance between the user and the access point, and a path loss index. We also account for the shadowing effect, which describes signal power fluctuations due to obstructions, modeled by a log normal distribution. This log normal shadowing is integrated into the path loss calculation, effectively expressing path loss in decibels with an added log normal random variable. Access point assignment is then determined by a condition comparing the user's current and predicted future locations, coupled with the SNR threshold. The accuracy of this prediction is calculated as the number of times a specific access point is selected, divided by the total number of prediction instances. Finally, task execution time is computed as the sum of the data size divided by the data rate and the number of instructions divided by the cloudlet's processing speed. The performance evaluation, conducted using the Green Cloud Simulator, demonstrates significant improvements. Our proposed method achieved a performance increase of 15.23% when compared to other existing methods. Focusing on execution time, we observed a substantial reduction. For instance, at a constant distance of 100 meters, a 10 megabyte data task had an execution time of 29.6 milliseconds with our method, compared to 35 milliseconds for the existing ENDA method. This trend continued with larger tasks. A 50 megabyte task recorded 39.7 milliseconds for our approach versus 50 milliseconds for ENDA. These figures consistently show that our method yields lower execution times across varying data sizes. Regarding prediction accuracy, our analysis revealed that access point 3 exhibited the highest accuracy at 66.2%, indicating its frequent and reliable selection as the next access point. Other access points showed lower accuracies, such access point 1 at 10%, access point 2 at 33.3%, and access points 4 and 5 both at 20%. This high-density data summary underscores the method's effectiveness in both reducing task execution latency and accurately predicting user mobility for optimal access point assignment. The theoretical implications of this work are substantial. Our model directly challenges existing paradigms in mobile cloud computing resource allocation by explicitly accounting for radio propagation fluctuation factors such as path loss and shadowing. Many prior models oversimplified the wireless environment, assuming stable connectivity within a coverage area. By integrating these dynamic location-dependent factors with user history, we provide a more realistic and robust foundation for predicting connectivity, moving beyond mere geographical presence to actual signal quality. This approach significantly contributes to the future research frontier in several ways. Firstly, it enables truly proactive and dynamic resource allocation, allowing cloudlets to anticipate user movement and prepare resources before a connection is degraded or lost. Secondly, it enhances the overall reliability and quality of experience in highly mobile and dynamic mobile cloud computing environments, which is crucial for real time applications. Thirdly, by demonstrating the tangible benefits of incorporating environmental radio characteristics, our work lays a strong foundation for the development of more sophisticated, context aware resource management systems in mobile, edge, and cloud computing. This shifts the focus from reactive problem solving to predictive optimization, opening avenues for more intelligent and efficient mobile computing architectures. In conclusion, our core contribution to the field is the development and validation of an efficient connectivity based mobility prediction model for resource allocation in mobile cloud computing. By meticulously integrating user access history with critical radio propagation factors like path loss and signal to noise ratio, we have demonstrated a method that not only accurately predicts the next access point, but also significantly reduces task execution times, achieving a performance increase of over 15%. This approach provides a more reliable and efficient mechanism for maintaining continuous connectivity in dynamic mobile environments. Looking ahead, we propose several specific directions for future research. First, we aim to extend the model to incorporate dynamic user velocities and variable cloudlet workloads, moving beyond the current constant velocity assumption to reflect real world complexities. Second, exploring multi objective optimization techniques would be beneficial, allowing us to simultaneously optimize for factors such as energy consumption, latency, and security alongside execution time and connectivity. Finally, we plan to investigate the application of advanced machine learning algorithms to adaptively learn and predict complex mobility patterns and radio environment changes, potentially leading to even more robust and intelligent resource management strategies.